Welcome back, everyone. Hope you're doing well. We've been talking about matrices as a type of linear operator, or sometimes a linear mapping, for us between two vector spaces. Namely, these have usually been finite dimensional vector spaces, Rn to Rm, whenever we're talking about matrices here. And the reason we've been discussing these is that essentially we're going to see in today's presentation, any finite dimensional vector space linear mapping is going to be described by a matrix. We'll have to be a little bit specific about what we mean by that. But we're going to go through some of those details here in this presentation today. So let's go ahead and begin talking about matrix transformations. We've already seen that any m by n matrix gives rise itself to a transformation, right? You can say if you are taking a matrix A and multiplying it times the input vector x that you put in for your linear transformation, the transformation does indeed satisfy the properties that it preserves addition and scalar multiplication. So this transformation ends up being linear thanks to those two things. Let's go ahead and see an example of that just to remind us. We usually would have a L of this vector here. And so this vector would be inputting a vector, something like x, y, z, when we might be multiplying it times a matrix A, like this one right here. This can fill in the role of our matrix A. And then what basically happens is, what is actually going on when we do this? What's happening, say, for example, to the standard basis vectors in R3 when I plug these things in? So here, for example, these vectors are inside of R3. What are we getting when we plug in the standard basis vectors in for X, Y, and Z? So for example, let's let E1 be 1, 0, 0, E2, 0, 1, 0, E3 be 0, 0, 1. What do you think is going to happen when we plug in L of E1? Well, we could go through and take a look at that. We could plug in X is 1, Y is 0, Z is 0 for just a second, see what we end up getting, and then we can do our little matrix multiplication here and figure out that the matrix that we, or the vector that we should get looks a little bit like this: 1, 3, and 0. The reason is that when you do your matrix multiplication on any given row, the only non-zero element in our input vector is the first one. So it only picks up one copy of the first element in each row. So algebraically, that's what's going on. What that means is we're only picking up the first element in each row. That is exactly the first column. So L of E sub 1 is the vector 1, 3, 0. That is the first column of the matrix A. LE2, on the other hand, now that you have just a 1 in the second place and zeros elsewhere, this is only going to pick up the second column and one copy of it. So L of E2 will be 0, 4, 5, and similarly LE3 will be 2, 7, 8. So you're noticing that the linear transformation given by this matrix multiplication picks up standard basis elements and then just picks apart the columns. L of E1, the first column; L of E2, the second; and L of E3, the third. These are the columns of our matrix transformation. LE1, LE2, and LE3 make the columns of our matrix here. So let's ask the question about going backwards. Let's rewind this. What is a linear mapping going from R3 to R2, for example, such that L of E1 is 1, 1, L of E2 is 0, -2, and L of E3 equals 3, 0. You may already have an inkling about this thanks to what we talked about in our previous slide. Let's go through and math it out. First, we note that whenever you specify where E1, E2, and E3 go, well, then you know where all of R3 goes. Because why? These three vectors span all of R3. That means any linear combination of E1 and E2 and E3 is also sent. We also know where it gets sent by this linear transformation. Here is a generic linear combination of E1, E2, and E3. And look what happens. L is a linear transformation. Linear means if you have addition signs inside, you can break it apart. And if you have scalar multiples, you can bring them outside. And that's exactly what you get for each of these terms on your inside of your function. So if we know where LE1, LE2, and LE3 go, we know where everything goes. Any generic value, any generic element of R3, X, Y, Z, we now know where that goes thanks to knowing that this is a linear mapping L. So if we know LE1, for example, is 1, 1, and E2 is 0, 2, and Z is 3, 0. We could go through and write out what vector that is when you add them all together. You should get something like x plus 3z in the first component and x minus 2y in the second component. If you put that all together into a matrix form, well, maybe you're not too surprised at what matrix we end up getting out of it. Look at each column of this corresponding coefficient matrix. That corresponds directly to the vectors that we had in the beginning. 1, 1 is the first column, 0, negative 2 is the second, and 3, 0 is the third. You can even check that this is exactly what we would get from this formula. X plus 3z comes from 1 coefficient of x, 0 coefficient for y, and 3 coefficient for 3. And that gives us our first row. Same thing for 1, negative 2, and 0 being the corresponding coefficients in the second component for our formula. Now writing everything as column vectors except as row vectors like we did back here. So when it asks what is the linear mapping L that makes this work, we can just write it as a matrix. So if we know where LE1, LE2, and LE3 go, we know where everything goes. And what's more, we see from this example, we can always write it as a matrix. This is exactly what this theorem is going to tell us. Suppose that L from Rn to Rm, now for just generic dimensions, N and M for our domain and codomain spaces, let's suppose that that is a linear map. Then there exists an M by N matrix such that the linear map is described as matrix multiplication by A. So this will satisfy any domain elements that we have in Rn. The columns of this matrix A end up being exactly the vectors LE1, LE2, all the way up to LEN, where you have the standard basis for Rn being plugged in for our linear map here. So if you know where these things go, you know how the whole linear map goes, because now you can formulate this entire coefficient matrix, right? So for example, here we have AX equals y being our function value outside of our linear map. The way we write this matrix equation out with all of its coordinates looks a little bit like this. You plug in an element from Rn. That's why this element, this vector here, has n entries in it. And then what you get out of it is something in Rm. And that's why right here we get our output is something inside of Rm. And then what do you have to connect the two? You have an m by n matrix. Here is that m by n matrix multiplied by something that is an n by 1. Gives us something that's an m by 1. And each of the columns here are meant to signify this is L of E1. This is L of E2. All the way up to this is L of E. This is for plugging in, so this is going to be L of E sub n. So these are our corresponding vectors that show us where the standard basis elements go. Another way to write this vector, if we would like, is like this, or rather, instead of this vector, if another way to write this coefficient matrix is like this. Maybe I could write it such as, let me get to a blank space here. I have one right down here. Oops, nope, I have it right over here, my bad. If I have y equals AX, and I write A to be basically with respect to each of the columns here, then what I could do is write my first column to be L of E1, right? And my second column is L of E2. And then finally, all the way up here, L of E sub n. This is another way for me to write that formula, this way of writing this matrix equation. So these two are meant to signify the same thing. Let's go back here to where we were before. There we go. So that is our theorem. Let's take a look at this in terms of an example. Let's let L be the linear operator, a different one now from R3 to R2, be given by L of A1, A2, A3 equals the vector A1 minus A2 and 2A3. Then let's construct the matrix A that we are going to need to signify how this linear operator can be written in terms of matrix multiplication via matrix A. Let's go through and construct the matrix A. But in order to do that, we're going to need to figure out where does this linear operator send E1, E2, and E3, the standard basis elements in R3. Well, to do that, we can just go through and calculate what happens when we plug in 1, 0, and 0. Should be just 1 minus 0 and then 2 times 0. So you see here we get the vector 1, 0, right? L of E2. So that's going to be plugging in 0, 1, 0. That should give us 0 and then 1 and then 0. Once we go through and plug all of those in. And if we do that, then we should get -1, 0 as that corresponding vector. And then finally, L of E3 should be 0, 2. Our first component now has zeros in A1 and A2. So 2 times A3 equals 2 times 1. That's going to give us 0, 2 for that vector. So once we know where those go, we know exactly what to do with them. We put them as columns of our 2 by 3 matrix to connect this matrix, this operator L, to matrix multiplication by this matrix A. So this is the matrix A that we are looking for. Okay. So this is that example one more time. Just going to flip through it real quick. And let's note that the example that's given here has a particular range space to it. Let's connect back to the previous presentations that we've had. The range space is given by the column space of this matrix. It is the span of the columns that are given here. And so we can rewrite it as the span of each of its vectors. And we notice that 2 of them are just multiples of each other. So we can throw that out of the span, since we can always make it a minimal spanning set in order to get to where we want to be. And then finally, these last 2 vectors are not scalar multiples of each other. So we know that this is a copy of R2. At least it is isomorphic to R2 as a vector space. Now, on the other hand, if we want to now take a look at the null space for this option, we know from the rank plus nullity theorem that the null space has a dimension of 1, right? We know the number of columns here. The number of columns equals 3. Because the number of columns is 3, and we know that the rank is 2, the null space has to have a dimension of 1, thanks to the rank plus nullity theorem. So if we want to solve for maybe what spans the null space, we can now solve for where this linear operator takes things to the 0 vector. That is, the 0 vector in R2 is going to be where you have 0 in each component of your 2 components for your vectors. A1 minus A2, for example, has to be 0, as does 2 times A3. Well, if 2 times A3 is 0, then we have to have that A3 is 0. And if A1 minus A2 is 0, we can add A2 to both sides and figure out that A1 and A2 just have to be the same thing. So the null space is spanned by the vector where A1 and A2 are the same. We could choose them both to be 1, for example, and where A3 is 0. So this gives us a spanning set for the null space here. So we can connect all of this stuff back to null space and column space that we've been discussing so far in this chapter. Now, since we're all continuing to connect back to what we've been discussing already, let's talk about changes of coordinates. Let's let V be a vector space. And let's consider 2 particular bases for V, just like we had before, V1 through Vn being one of them, and U1 through Un being the other. And let's let G1 and G2 be, as before, the coordinate mappings corresponding to each of these bases. Remember that the way that this worked is that you took a vector V and you wrote it in terms of the scalars that you would get for it, in terms of the basis that you were given. So for example, you might have been given something like this if you're working inside of, say, the basis for U given here. So the composition going from, remember, we had to go backwards up G1 and then downwards to G2 to give a change of basis from Rn to Rn, one that we were more familiar with. And once we had something like that, we got a matrix, an n by n matrix called the transition matrix between these 2 bases. The way that we were able to say, okay, how do you make this actually a transition matrix we can find? Well, the columns of U are the coordinates of the vectors from the first basis that we were working with respect to the new basis that we were going toward, okay? Now, a matrix of a linear transformation can throw a little bit of a wrench in things. So far, we've only talked about linear transformations going from Rn to Rn. Like we've had a couple of examples where we had to go from R3 to R2. And in those cases, we just have basically a way to construct the matrix going from R3 to R2. That's all that we have to work with. Well, if this is the matrix that we have, if instead if we're going between 2 abstract vector spaces, say V and W, well, then we need to do the change of coordinates trick in order to get these to look like something in terms of Rn. So that's what we're going to be doing here. We're going to, again, flip the direction of G1 and then pass it through our new linear transformation, F, and then finally go back to G2 in order to get us our linear mapping in terms of the coordinates for V and W, respectively. So this is a linear mapping that we can now talk a little bit about. So it's going to be represented as an m by n matrix that we can go through and find. We're going to call A the matrix of our linear transformation F. F, again, is the linear transformation between two vector spaces, abstract vector spaces. But for each vector space, we're going to assume that it has a finite dimensional basis so that we can make a coordinate mapping from V to Rn and then also from W to Rm. Once we put all of those things together, we're going to get a linear mapping between two spaces we know a lot about so that we can create a matrix between the coordinates for each of these. So let's dive into this terminology for just a second before we get into an actual example. First, we said that A is the matrix of our linear transformation F with respect to the bases, and you can see the order going on here. Here's our first basis. This is the first one that we are starting from. This is the one that lives in this space that gives us coordinates in terms of Rn. And then our final place that we're resting, our final basis place is going to be for the basis that in terms of coordinates in terms of Rm. So that's going to be from beginning to end, V1 through Vn to W1 to Wm. Just note the slight little change in letter there since we had U before, just no real reason for it, just to kind of specify that this is slightly different. Now, columns of A are going to be just like in the previous slide where we had the columns of A being the way that you could write the original vectors in terms of the new basis elements, the new coordinate system that you're working in. These are going to be coordinates of vectors f of v1 and all the way up to f of vn. That is plugging in the vectors v1 through vn with respect to our new basis. Think of this as like how before, when we were just working in the more specific example of Rn to Rm, this F you should be thinking of as our linear transformation L, and then what we're plugging in are the standard basis elements, LE1, LE2, so on and so forth, all the way up to wherever it ends. So that was where we were starting before, was in that standard basis. So when we want to write it with respect to a new basis, we start with these columns here. So we're going to try and combine these two now. We're going to talk about how we've been doing the linear transformations earlier in this spot, and also think about how we might do this with respect to more abstract vector spaces. Now, the thing is that not everything is that big of a deal when it comes to how you write your coordinates. For example, remember that the polynomials, the space of P3 and P2, which are the polynomials that are a degree less than or equal to 3 or 2, respectively, have very standard bases. So we aren't going to have to think too much about how we do change of coordinates in these spaces. We're just going to have to remember that we're working with respect to the standard bases for each of these spaces, 1x, x squared, and 1x. Let's go ahead and find this matrix of transformation, the matrix of this operator D. So here, let's take a look at what the differential operator here, D, is. It looks like it just takes the polynomial and it takes the derivative of it. So let's see what happens when we plug in our original basis elements into this derivative vector. Well, what's going to happen to 1? When I take the derivative of 1, I'm just going to get 0. That's just me plugging in the function 1 in for this place and seeing what I get out of it. That's exactly where this operator is going to send the first basis element inside of P3. It's going to send 1 to 0. dx, on the other hand, that is now a function that has a derivative of 1. So this one is going to get sent to 1 here. And then finally, dx squared is going to get sent to 2x. Okay, so that's because the derivative of x squared equals 2x. So first, let's think real quick. How do we write coordinates for each of these functions that we have? Remember that we're now going to be writing them in with respect to our new basis. So for example, 0 is going to be just a two-dimensional vector, 0 to 0, because that's where we're ending up. We end up in the polynomials of degree 2 or less, and that's just going to be things that have polynomials of 0. I'm actually just now realizing that there is a little bit of a difference between how we've talked about these spaces before and what's up here on the screen. So let me actually make a quick change here to what D is actually being put. Let's just change what these domain things are and what the codomain is. So if you will allow me this little allowance, let's take the polynomials of degree less than or equal to 2. for this space. That way we're working with a space that has dimension 3. This should be what we expect because this is how we've been defining these spaces of polynomials so far in this class. Then this is going to be the polynomials of degree less than or equal to 1. Now it makes sense that this space is only spanned by 1 and x. We wouldn't be able to get x squared in there, for example. So now this is a space of dimension 3. This space has dimension 2. And now we can continue thinking about what kind of matrix we should get out of here. We should expect a 2 by 3 matrix. Let's see if that's what we get. So we start by trying to figure out, okay, how are we going to write the function 0 in terms of the bases 1 and x? Well, there's 0 constant term and there's 0 x term, so it is a very nice vector there. What is 1 going to look like with respect to this basis? Well, it's going to have 1 as its constant term and 0 as its x term. Because of this, dx should be equal to 1. And finally, dx squared equals 2x. So this should be equal to 0 constant term. That's with respect to the basis element 1. And then how much for the basis element x? It should be 2. So if we put all of these columns together, this gives us our matrix here. A sub d equals this matrix. This is the matrix of D. The mater D. So this is the matrix that we're working at for this particular operator. Let's go ahead and get some practice with this. I want us to see what this sort of thing looks like. So let's take this matrix AD. I'm going to go ahead and write it down again. It should have 0, 1, 0, 0, 0, 2. And what's going to happen is we're going to be plugging in an element that comes from the polynomials of degree 2 or less. So it's going to be written in terms of the standard basis 1x and x squared, right? So we'll call that a1, a2, and a3. Okay, so what's going to happen is now we have written the matrix that goes with this linear transformation. So it's just going to be this sort of matrix multiplication. So let's try this out. Let's go ahead and plug in an example. What happens if we take the derivative of the polynomial inside of P2? That is going to be 2 plus x minus 3 squared. Well, if we take this derivative, we can just go through using our sum and power rules and get something like 1 minus 6x, right? Well, what would that matrix look like in terms of its coordinates? What could we go through and plug in here for a1, a2, and a3? Well, our constant term, remember we're writing this in terms of this standard basis. So our constant term is going to be 2. Our x term is going to be 1. And then our x squared term is going to be negative 3. Let's see what answer we get if we plug it into this matrix of the derivative here. If I go through and multiply this through, I should get 0 times 2 plus 1 times 1 plus 0 times negative 3. That's 1. And then if I multiply this column by the column vector, I should just get 2 times negative 3, right? So that's just going to give me negative 6. And if I write that coordinate in terms of standard basis for P2, then I'm going to get exactly 1 minus 6x. See, what's going on here is that we are writing the determinant, not determinant, the derivative with respect to all of this in terms of a matrix so that we could be doing matrix multiplication here. And it turns out very cool that we can actually write the derivative in terms of a matrix like we have right here. Okay, so this is something that is going to be a neat little recurrent theme for us here. Whenever we're talking about linear operators like the derivative, we can now go through this matrix and ask the questions like, okay, what is the range of this particular operator? This is going to be what? The span of these columns here, because these columns are going to be let me repeat myself here. We're going to take the span of each of where the operator takes the standard basis elements of our space P2. So for example, it's going to be taking d of the function 1, d of the function x, and d of the function x squared, because this is where the standard basis elements are coming from. So this is the span, this is the column space of this matrix. So it's going to be the column space of AD. So that's going to be the span of these particular vectors here. Well, it's going to be the span of 1, 0 and 0, 2, which, by the way, is all of P2. So that's all of our range space here. It is all of the polynomials of degree less than or equal to 1. Sorry, it should have been P1, not P2. I got confused from what we had there before. So it should be the span of just these two things. And then what is the null space of this is also an interesting question. We can go through and do the same thing we've done in the past where we try and get a row reduce this down to see what are the free variables and things like this here. And if we go through and do this, finding its range or its null space, then we should see that this column right here just is going to have zeros in it. That even after doing a row reduction here, we're still going to have zeros in our first row. So the null space of this operator should actually just be the null, or the, maybe I should say the kernel of this operator should be the null space of our matrix AD, and that's going to just be the span of 1. The span of 1 because that's going to be the non-pivot element here. All we want is just for to take that vector and take a look at its span. So that gives us kind of like what we're looking at in terms of our rank and nullity formula. Again, we have a two-dimensional column space and a one-dimensional null space, and that adds up to our 3 columns for this matrix. All right, so neat little thing there in order to try and connect us back to what we were looking at before. Let's keep going with some other problems here. Let's consider a linear operator on the vector space of 2 by 2 matrices given by, well, we already have a matrix operator going on here. L is a linear operator, so it can be written in terms of a matrix. We have a 4-dimensional space in terms of the 2 by 2 matrices that we're beginning from, and we end up in the same space. Remember, linear operator means you go from one space to the next, and it's exactly the same. So L is going from M2 to M2. All right, so let's see if we can find the matrix of L with respect to a new, or with respect to the standard basis in terms of E1, E2, E3, and E4. Okay, so we know what this linear operator is, or what it's defined to be. Let's see if we can figure out what the desired matrix is when we try and create the matrix of L. Okay, so let's see what's happening. Now, how big is this matrix going to be? Well, we're going from a 4-dimensional space to a 4-dimensional space. We're going from the space of 2 by 2 matrices to 2 by 2 matrices. What we're going to have to do is write our diagram a little bit like this. We know that M2 to M2 is where our linear operator is going, right? And we know that we can write each of M2 in terms of their coordinates, in terms of R4, the dimension of each of these. So we're going to have some sort of G1 and some sort of G2 here. So what we're going to expect is this operator, once we reverse this direction and take it around through here, is going to be some sort of transformation going from R4 to R4. Well, that transformation is going to be described by a matrix, and it's going to have 4 rows and 4 columns. So we're going to need a 4 by 4 matrix from each of those. So the columns of each of those are going to be given by LE1, LE2, LE3, and LE4. All right, let's take a look at what each of these are going to be. Okay, first, we need to make sure that we keep in mind this order. E1 is what we're going to be plugging in first. So we're going to be plugging in 1, 0, 0, 0 for this operator here. So that's what's going to get plugged in right here. We're going to see that in just a second. Here is exactly what that is. We write that out and we get 1, 0, 3, 0 as our matrix. If we write that out in terms of the standard basis that we have just been given for the 2 by 2 matrices, that's 1, 0, 3, 0. That is the coordinate that we're looking at. So we should expect this to be a column in our matrix M sub L. In fact, this should be column 1 because this is what we're plugging in for E sub 1. If we keep going through this, we're going to get a couple of other columns too. 0, 1, 0, 3, 2, 0, 4, 0, and 0, 2, 0, 4. All of this and what it's coming through is seeing what happens when I plug in one of my standard basis elements in for my linear function. Once I do that and I look to see what happens, for example, here in LE3, if I multiply through, I get 1 times 0 plus 2 times 1. That gives me a 2 right here. If I multiply from the bottom row and this first column, I should get 3 times 0 plus 4 times 1. So that should give me 4. And then I know I'm only going to get zeros in the second column. So that's going to give me that coordinate. And then continuing that on throughout each of these other examples, we're about to see what our ML is going to be. You can see our first column is indeed the first column that we had isolated right here. And the second column that from LE2. This is because we're just going through and writing this in the same format as we have been in the past. LE1, LE2, all the way up to LE4. There we go. So this is our matrix operator. And this is a little bit interesting because we haven't really thought about this. We may have thought, oh, okay, well, maybe the matrix of this linear operation is just a 2 by 2 matrix, just like before, because we were just working in 2 by 2 matrices there. The reason that it was different is that each space of matrices has 4 basis elements, and we have to know where each of those basis elements gets sent. So the relation that's given here between all of the elements x1, y1, z1, w1 in the range of this linear operator, right? Given something in just the space of 2 by 2 elements here, this is equivalent to a relationship from R4 to R4. So this, being our 4 by 4 matrix, is telling us that what that relationship looks like. So we could write this matrix multiplication in terms of x, y, z, and w in terms of R4 as well. So a neat little connection here as some sort of way of mapping R4 into itself by using matrix multiplication in the set of 2 by 2 matrices. Pretty neat little thing here. Let's go ahead and keep going here, and let's go ahead and see some more linear operators in what we're working with here. Let's consider another linear operator with some of this basis stuff going on still. But this time, let's go ahead and consider one going from R2 to R2. So we know that we're working with a 2 by 2 matrix for the matrix of this linear operator. But let's do it with a little bit more of a strange basis. Let's find the matrix of L with respect to the basis V1 and V2. Now, before we begin, let's ask ourselves a question, because I thought that whenever I had to have a matrix of a linear transformation, I actually needed to have 2 bases. Thought I had to have one from where I was beginning. That was our V1 through VK, or V1 through Vn. And then another one had to be from W1 to Wm. I thought I had to have another basis for my same space. Not for a linear operator, we don't. For a linear operator, when we're going from one space to itself, it's okay for us to consider each one being written in respect to the same basis. So this is going from the basis V1, V2, this strange new basis, all the way to R2 again with respect to this new basis. Now, that is certainly not how this matrix is written. Right now, XY is just going to be written in terms of the standard basis here. So first things first, we've got to figure out a way to translate things inside of this basis with respect to V1 and V2 in terms of our standard basis. So basically what we're going to do is this. We're going to take our function from before. Here's V and here's W. That's what we're calling R2 and R2 right now. We're writing these coordinates in terms of R2. So we have these pictures here. Here's R2 again. And then here is our linear transformation L. So here's the picture of what we have. These, of course, are the coordinate maps from before, these pictures on the side. So we're going to start by trying to write let's make sure we get this straight here because it's a good idea too. We're going to start by writing new vectors in terms of the old ones, then apply this linear operator, and then get this back into our original basis because we are starting in the basis of V1 and V2. We're starting here. And we want to end up in that basis as well. So we want to be writing in terms of this. So this is the map sequence that we're going to be taking. So let's go ahead and say N is going to be that matrix for the linear operator L. Now, columns of N are going to be, thanks to what we were discussing before, this is a succinct way of putting it, the coordinates of the vectors LV1 and LV2, those are the elements for our beginning basis, LV1 and LV2, with respect to the basis V1 and V2. So once we get these vectors, LV1 and LV2, we're probably going to be getting them, since we're going to be popping them in here, we're going to be getting them in the standard basis coordinate system. And we're going to have to make sure that before we end, we convert back to the basis coordinate system of V1 and V2. So let's just make sure that we're keeping that in mind as we move forward. Let's start by calculating LV1 and LV2. So V1 is 3, 1, so I can go through, plug that in, and just see what that ends up being. I'm doing a 2 by 2 matrix multiplication times the vector 3, 1, and that gives me the vector 4, 1. Okay, 4, 1, I'm going to go ahead and keep in mind. LV2, on the other hand, is going to give me 3, 1 once I go through and multiply it through. Now I have 4, 1 and 3, 1 as what LV1 and LV2 are, respectively, but I do not yet have them in the basis V1 and V2. So I've got to think, okay, how am I going to write LV2, for example, in terms of the coordinate basis of V1 and V2? Remember that the way that we've done this is we've written LV2 equals some alpha times V1 plus beta times V2. And we basically want to figure out what alpha and beta are here. Great news on LV2. LV2 is 3, 1, and guess what V1 is? It's 3, 1 as well. Because of that, I know that I don't even have to solve this equation. Alpha is going to be 1, and beta is going to be 0. So LV2 equals V1. That's going to give me a column somewhere in my matrix corresponding to the second column, in fact, of 1 and 0. So I could go ahead and write that down if I would like. I know that the second column of this matrix N is going to be 1 and 0. Now I need to still figure out what LV1 is going to be in terms of these two basis elements. So I go through and set up a system of equations. LV1, remember, is 4, 1. And since V1 is going to be the matrix 3, 1, and then V2 is going to be 2, 1. I'm attempting to solve the following system, taking the column V1 and V2, writing it in here, and finding an alpha B such that this is equal to 4, 1. So I can do this using Gauss-Jordan system of equations, elimination, substitution. Eventually, once I find that alpha and beta, I know alpha is 2 and beta is -1. Well, that's going to fit in to be my first column because that's LV1 written in terms of our new basis. And indeed, that is exactly what we get here for N. And this change of matrix formula is given in this sort of way. You may have noticed that we did something interesting here. We had to convert everything back to the standard notation before we went and did things from our changed basis on this. Let's go ahead and take a look at that picture one more time that we had drawn up there in the top right corner. Let's say, for example, we have a basis A that we're very comfortable working with. Let's say we have a basis A that we're comfortable working with here, but we want to write it in terms of things that are in terms of basis B instead. So how would we go through and do this? Well, if we want to start with something down in here and want to end up over here, and this map is a little bit elusive to us, we'll call it B. That was the map N from before. Then what we could do to try and figure that out is we could go up real quick and call that U inverse, where U here is going to be the map given by our change of basis. This is the coordinates matrix that we would get from converting one basis into the other. We've gone through and talked about how to do that in our previous video. So there's U inverse. And then we would multiply by the matrix A. That would be A being just the actual matrix map, or whatever map is given to us, the linear map going from one space to the other. So that's just taking vectors V into L of V, so whatever that matrix is. And then finally, we would multiply times U again to get us back into, again, U is the coordinate matrix here, get us back into our original basis. You may have seen this format before. This is the way that you get similar matrices. Similar matrices. Similar matrices are matrices where you can multiply one matrix by, on the left by another matrix U, and on the right by inverse matrix, so U inverse, and gets to another matrix over here. So we say A and B are similar matrices over here. That's exactly what we have down here. B is U, A, U inverse. In fact, we could have done this the opposite direction to find A if we would like. We could have gotten that A was U inverse BU. Now, why is this interesting to us? Why do we want to study similar matrices? Let's talk a little bit about what happens. What are some properties of similar matrices? This is where this starts getting interesting, because all of these linear transformations, in particular with respect to different bases and things, now are starting to connect to something that maybe we've heard a little bit about before, this theory of similar matrices. Let's go ahead and take a look here. Let's write that A is U inverse BU, just like we had it right up there. What is the determinant of A in terms of B? What is the determinant of A in terms of B? Well, we know it's going to be the same as the determinant of this right-hand side. Going to be the determinant of U inverse BU, given here. Now, the determinant is neat. Determinant is if you have two matrices that are multiplied together, then you can just multiply the determinants together to get the entire thing. So determinant of U inverse, determinant of U is another way that we could go through and write this. So determinant is neat like that. I can also switch these around if I would like. Determinant of BU, determinant of U inverse, and that's because we're just multiplying numbers now. A times B is B times A. And I can go backwards. Now that I have two determinants being multiplied together, I know that that's the same as the determinant of the product. The reason that I did this little switcheroo here is that now on the inside, I have B times U inverse. This gives me that the determinant of A is equal to the determinant of B. Another neat little application here, by the way, that we could go through and see here is that the determinant of U inverse is going to be 1 over the determinant of U. We can go through and play around with this, say, for example, by breaking apart the determinant of B times U into the determinant of B times the determinant of U. Well, the determinant of U times the determinant of U inverse is the determinant of the identity matrix, and that's just going to give us 1. So we get this little fact from doing some playing around like this as well. But similar matrices have the same determinant. This is a neat way for us to be able to connect things that are changes of basis from one another. And whenever you have two matrices A and B with the same determinant, or if there are different determinants, for example, we know that there is no change of basis that allows one to be a matrix of a linear transformation in terms of another set of bases there. But how does this connect back to what we were doing before? Let's return to that same linear operator that we were working with previously. And let's see if we can solve it now with the notion of similar matrices. Let's let S be the matrix of L with respect to the standard basis. With respect to the standard basis, well, we already know what S is, in fact. This was in the standard basis, our domain was, and then our range, that's also going to be in the standard basis. That is because there was no basis specified to begin with. So our matrix of L is just going to be the matrix we're multiplying by. So the matrix of L in with respect to the standard basis is just 1, 1, 0, 1. And let's let N be the matrix of L with respect to V1 and V2. So that's going to mean, okay, how do I write the matrix of L, or how am I going to write the matrix of L with respect to this basis? That's what the question is trying to ask. So we're trying to figure out what this N is. But remember that we were talking about one more matrix in our previous slide. We were talking about the coordinate basis, right? The coordinate matrix, the way that you would write one matrix, this basis in terms of the standard basis. That was what we're going to call U. U is the transition matrix going from our new basis into our old basis, V1, V2 into our standard basis. What is U then? Well, if we're going from our new basis to our old basis, we do not have to take U inverse. Instead, we just write the first vector as the first column of that matrix, that's 3, 1, and then the second vector as the second column of this matrix, that's 2, 1. So that should be our transition matrix U. Well, what did we say? We said that the matrix between the two new bases that we have, N, could be written as, well, you could go through and write it as U inverse times S times U. That was the formula that we had before. Let's take a little bit of a peek and remind ourselves that this is the correct order by going back up to our slide up above. Remember that N, the thing that we're looking for, is going to be this notion of trying to connect between kind of like our weird bases, if you will, right? Now, U, the matrix that we're working with, takes us from our new basis into our old basis. So checking on that real quick, our new basis into our old basis. So this is going to be our U right here. This is U. So even though it says right here that this is a matrix U, we know now that U is taking us from our new coordinate space into our old coordinate space. And this makes more sense given our picture here. Then we've got the matrix in terms of our standard vector space. We've been calling that one S. And then finally, we need to revert what U is. We need to go U inverse here. And if we compose all of these maps together, we should get U first, then S, and then U inverse. Composing all of these maps should give us this map down here, which we have been calling N. So indeed, this works very nicely with our picture here. So N is U inverse times S times U. So instead of having to do kind of a multi-step process, I know exactly what matrices I need, and I know exactly how they need to be multiplied together. They need to be multiplied in order to find the similar matrix n. So we're going to multiply U inverse times S times U. Here is U inverse. I can go through and invert this matrix, noting that it is a determinant 1 matrix. I can just flip the diagonal entries and negate the off-diagonal matrices or entries here. Multiply times S and then multiply times U. Putting that all together, we'll take a look. We've got the same matrix that we had in solving it the other way. So a pretty neat way of using similar matrices to try and make this connection here. So this means that similarity of matrices is likely something worth studying. And we're going to want to talk about it a little bit, especially before moving on. So first things first, let's make sure our definition is clear. We're going to say an n by n matrix B is said to be similar to another matrix of the same size, n by n as well, if B equals S inverse times A times S for some non-singular n by n matrix S. Okay, so what we mean by non-singular here is that, well, one, you need to be able to invert this matrix. Otherwise, S inverse does not exist. Remember, non-singular means invertible, or that its determinant is non-zero, right? We're in that kind of world there. Now, two n by n matrices are similar if and only if they represent, just like what we were seeing before, the same linear operator on Rn, but just with respect to different bases. So all linear operators are kind of related in that way. It's just you had to change your coordinate space whenever two matrices are similar there. So this gives us a little bit of a theorem. Let's talk about what that theorem is. That theorem is that the similarity is actually an equivalence relation. Remember how equivalence relations work? You need three things for an equivalence relation. First things first, everything in your space has to be related to itself. Two, if you have A is related to B and B is related to A, then in fact, or rather, if A is related to B, then B is related to A. And then finally, the transitivity relation. If A is related to B and B is related to C, then A is related to C. So we are saying essentially that similar matrices have an equivalence relation going on. Let's say, for example, that A let's ask the question first, is A related to itself? Can you multiply a non-singular matrix right over here and the inverse of that matrix over here such that you get A back? You sure can. You can multiply both sides by the matrix I. I times A times I is the matrix itself. So you can go through and verify that everything is self-similar. Same sort of deal, or is self-equivalent. Same sort of deal. If B can be written as S inverse AS, what could we do with A? Well, we can solve for A here and get that SB S inverse is equal to A. So whenever we want to say if these things are similar, we could have replaced S with something like T inverse and gotten to get the same similarity formula like we had there. And that's going to show us 2. Finally, composing similar matrices together will allow us to see the transitivity relation. If you have one is similar to the other thanks to S, and then another is related to a third thanks to T, then multiplying those things together will allow us to get from A to C via a similarity relation. And that gives us 3. So a neat little equivalence relation stuff there. So we can now, thanks to the fact that equivalence relations induce a partition on our space, we can now say the set of square matrices, n by n matrices in particular, is partitioned into disjoint subsets. And we can call those similarity classes, such that all matrices in the same subset are similar to each other, while matrices from different subsets are not similar. That's the notion of a partition. So that is our theorem there. It's good to see that there's a little bit of a proof written down, first using our identity relation, and then using S inverse as the matrix that we're multiplying by for part 2. And then you could see what I meant by kind of quote unquote composing or multiplying matrices to make a transitivity relation happen here in part 3. So if A and B are similar matrices, then they have the same determinant. We've already seen this. We've gone through and kind of proven that one. They also have the same trace. Trace is a new thing for us, perhaps. Trace is the sum of the diagonal entries across the matrix. They also have the same rank, meaning they have the same number of elements as one another. And then finally, they have the same nullity, the same dimension of their null space. So let's do one more example of this to finish this off. Let's talk about how similar matrices can help us figure out how these maps work with each other. Let's go ahead and define an operator on R2 in the following way. Let's say that I have a line. and that line is spanned by the vector 2, 1. So I'm going to take this line right here. And let's say that I'm going to make L the linear operator that does the following. This is going to be the operator that flips vectors across the line spanned by the vector 2, 1. So L is the operator that flips vectors across that line. So here's what I mean by that. For example, if I have something right down here, then what I'm going to do is take that vector and I'm going to flip it across that line. I'm going to find a little orthogonal connector from this point to that line. I'm going to measure that distance, and I'm going to repeat that distance over here, and I'm going to put a line over there. You can imagine that a reflection is literally a mirror reflection. We want it to be at the same distance over here to this line as it is from this point to this line, the place where it's going to end up. So I want that flip to take place. Now, here's the neat little thing. If I want to flip a vector that's already on the line, so like, for example, if I want to flip 2, 1, then what's going to happen? If I flip 2, 1, well, it's already on the line that's spanned by 2, 1. It doesn't go anywhere. Its distance to the line 2, 1 is 0. So this just gives me the same vector 2, 1. Okay? Now, I want another vector to try and plug in here because 2, 1 doesn't quite span R2. I would like to try and plug in another vector here that I know where it ends up going. What about this? What if I plug in the vector, let's do 1, -2. The reason I'm going to plug in the vector 1, -2 is that these two vectors are orthogonal to each other. 2, 1 and 1, -2 are orthogonal to each other. I could confirm this by, say, taking the dot product between these two vectors. Let me draw 1, -2 down here. You can see that these two vectors are going to be orthogonal. And what does that mean? When I flip over this arrow across the line spanned by 2, 1, what am I going to get? I'm going to get a vector of exactly the same length across the way from there. So this is now just going to be in the opposite direction of our original vector. It's going to go -1, 2 there. So what's happening here? What is my linear transformation doing? Well, in terms of the basis of 2, 1 and 1, -2 that I have formed here, what's happening? Well, first one, in terms that, let's write this as our matrix of our elements here, A of V1 and V2 with respect to V1 being 2, 1 and V2 being this vector right here, V1 and V2 making a basis of R2 for me. So hence I can make a matrix of this linear transformation with respect to this basis. What is this going to be? Well, it's going to take any component, anything that is in terms of 2, 1. Again, this is written in terms of V1 and V2 here. Oops. So this little column vector I should be thinking of as one copy of V1. Well, whatever this matrix needs to do for this column is it needs to send it to itself. It needs to send 1, 0 to 1, 0. So what is this going to be? I know that it's going to send V1, this is just one copy of V1, to itself. So what does this end up being? This is going to be the first column here, 1, 0. This is L of my first vector here, V1, with respect to the basis of V1. It sends V1 to V1. So that should look like this column 1, 0, right? So that's what that one's going to be. So where is A of V1, V2 going to send V2 in terms of the basis V1 and V2? This is just one copy of V2. Well, it's going to send V2 to the negative of itself. So if I'm writing that basis element, it should look like this, 0, -1. So writing that part of this matrix, I should get something like this. Here is the matrix of this transformation written in terms of V1 and V2. Now, usually this is not acceptable. I want to try and write everything that I can in terms of its standard basis. I want to write everything in terms of the standard basis. So if this is what A V1 V2 ends up looking like, what is A V1 V2? That's the question that I want to try and answer. Well, let's see if we can do this. Well, first, we would need a matrix that takes us from the old into the new. We would need something that takes us from a vector xy and rewrite it in terms of our basis elements v1 and v2 so that we can start plugging it into a v1, v2. So we would need a transition matrix to help us to do that. Now, which one helps us transition in from the old to the new? Well, if I'm thinking about that correctly, and by thinking about it, I mean looking over here at my notes. That's how it goes whenever we do our homework together here. We should be getting something like, let's take a look. Should be getting something like U, I believe. So again, U here being the transition matrix from the old E1, E2 into the new. So here, for example, U should be given in terms of that matrix. Okay, perhaps that's U inverse. I'll go back and check on that before we finish this video. And then I'm going to want to multiply that times the matrix of my linear transformation. That's going to be in terms of V1 and V2. And then finally, I'm going to want to invert that. Whatever matrix I multiplied on the right here, I'm going to make sure that I'm multiplying times the inverse so that I'm going back into my standard basis in terms of E1 and E2. Okay, I'm back. I was indeed that the inverse needed to be on this matrix closest to our xy, our standard basis here. And the reason that this is, and I'll go ahead and reiterate how I try and remember this, because I think that keeping these two things straight can be at least tricky for me, is that whenever I'm trying to convert from a new basis back into the old basis, I could just go through and multiply times my vectors, right? So if I have my vectors, for example, here, which are 2, 1, and 1, negative 2, as my vectors for what is the new basis that I'm working with. If I want those back in the old basis, I just have to do a linear combination with respect to those two vectors. Well, how do I do a linear combination? A linear combination with this? Well, I just do my first column to be my first vector here, and then my second column to be my second vector for what v1 and v2 should be respectively. That is the vector u. That gets me from my new basis of v1 and v2 into my standard basis. So this is the matrix u that needs to go in there. This U inverse, on the other hand, needs to be the inverse of this matrix in order for me to calculate that. Now I've been able to use the notion of similar matrices to try and compute what this matrix of transformation actually is in terms of the standard basis. So that kind of gets us through a little bit of some examples here of seeing all of these different ways of trying to make this work. That'll do it for today's video. Thank you for watching. Have a good one.